All right, so we are in, let's see here. We are in this book right here, Generalized Linear Models with Examples in R. We're in Chapter 2, and we are on question 2.3 right here. Okay, so this is a, in the book, this has an asterisk or asterisks next to it, implying possibly that it's hard, but I think more specifically that it requires matrix manipulations, so linear algebra. So if you're not familiar with linear algebra, then you won't really be able to do this one, but maybe you can kind of get a sense of it by working through this with me. So, okay, so earlier in the book, it kind of shows how to derive the beta coefficients in when we have multiple predictor variables, many x's. Okay, but you can do this with just one x variable. But when you have multiple variables, then it's more convenient to use this matrix notation. Okay, and so we'll go through these in a second. But one of the matrices that we get out of all of that is this guy right here. Okay, XTX, or when it's weighted, XT, or the transpose of x, times the weight matrix times x. Okay. And so the first thing that we're meant to show is that this, in simple linear regression, meaning an intercept and a slope, equals this right here. Okay. And that, so this, or that little expression right there is part of our expression for the beta vector, which houses both the intercept and the slope. And the beta, or I'm sorry, the slope intercept beta 1, given that this is part of that expression for the beta vector, that beta 1 comes out to equaling this. Okay, so so let's first try to get this expression right here. Okay, so I'm going to define our matrices. So x is right here. So we have one column for the intercept, and then one column for the observed predictor variable. And so now when I transpose this, I just knock it over onto its side, and it becomes this right here. Okay. And then my W matrix is a diagonal matrix, right? So that's the weight of the first observation, the weight of the second observation, and so on. So just this diagonal has something, and then all the way to the weight of the nth observation. Everything else is zeros. Okay. So with just basic matrix multiplication, so if I have, so here's my xt, my w, and my x. Okay, so the first thing I'll do is I'll multiply my x and w, and now I have xt and then the matrix that I just formed. And then when I multiply all that together, then I come out with this matrix right here. Okay, so now when all w's, all the weights equal 1, as was specified in the problem, well then this matrix simplifies here. And so just to kind of think about that, so if all of my w's equal 1, and I have n w's all equal 1, well then the sum of my w's equals n. And that's, part of what we wanted to show in the question, right? Okay. And now similarly, so I have the weight times the observed x variable. Well, if all of the w's equal 1, then this is just the sum of all of the x variables, and so I get that. Okay, same thing on this part over here. Okay, and then right here, if I have the sum of all the wx's squared, and all the w's are 1, well then this is just the sum of all of the squared x's, and that's what I have here. Okay, and so that's what we wanted to show for that first part. So we've done that. Okay. Now, the next thing that we want to show is that beta is equal to this expression right here. So given that we've derived our expression for x transpose wx, we want to show that this expression for beta 1, the slope, is implied. Okay. So I'm going to, in order to do this, we're going to derive both the intercept and the slope, because again we're using matrix multiplication, and when we do that we kind of get everything together. So now in matrix multiplication, our expected value mu is equal to x beta. Okay, and I'm going to talk about what these are in a second. But then that means that the deviations of our predicted values from the actual values, y minus mu, is y minus x beta. Okay, and so here mu is a vector with n components. So if I have n observations, then I have n predicted values. I have x, which again is the predictor, the predictor variable for each observation, times its coefficient. Okay, so x can be a matrix. In fact, we already saw that x was a matrix. Okay, and beta is a vector. In fact, beta looks like this. Okay, so it has p plus 1, elements, where p is the number of predictor variables, right? So I have one predictor variable, one x variable in this case. Okay, the intercept is not a predictor variable. Okay, and so p in this case is 2, one for the intercept and one for the slope. Okay, if we had more predictor variables, then p would get bigger, and so on and so forth. Okay, so now in matrix notation, our sum of squared function s becomes this guy right here. Okay, so that's a deviation, weight matrix, deviation. Okay, so that's our sum of squares. Notice we have two y minus x betas, and so that's kind of like squaring that, weighted by, well, the weight matrix. And so then if I expand this expression out, right, so I take y transpose times w times y, and I get this. Okay, I take y transpose times w times x beta, and I get this expression. Okay, and you can just kind of keep going, right? So now negative x beta transpose times w times y, Okay. So I'm going to, just to simplify this parenthetical transpose x beta, I can just take the transpose inside of that, and it converts the x beta transpose to beta transpose x transpose. So I did that here and here. Okay, very good. All right, and so now what we need to do is we need to take the derivative. So remember that when we want to find the beta, the appropriate beta, I need to take the derivative of my sum of squares and set it to 0. Okay, so that's what I'm going to do. So my derivative of sum of squares over beta, okay, is, so I'm going to take the derivative of this expression up here. So this first one is 0. Okay, so there's no beta term in there. So its derivative with respect to beta is 0. Now I take this expression and I take its derivative with respect to beta. So here's a beta right here, and by the product rule, okay, I just get this expression right here. Similarly here, okay, I take this. Really, I guess I maybe should transpose it, but it doesn't matter. So, but I have one beta, so what's left is XTWY. Okay, and then here I have two betas, so it's kind of like beta squared. Again, in matrix multiplication, it gets a little bit squirrely because we often take something transpose times itself again to represent a squared, and here we see beta t beta, so that's like beta squared. And again, with derivatives, that would be like taking beta squared, so it would be 2 and then times the inside expression, etc. Okay, so anyway, the derivative for that last part is this. Okay, well, it turns out that this expression and this expression, both highlighted, these are actually equal to one another. Okay, so I actually just have two of these. I have negative 2 of these. So I have negative 2 wt, or I'm sorry, negative 2 x transpose wy, and then 2 xtwx beta. Okay, and remember, I want to set that to 0, and when I set that to 0, then I get the expression where this part and this part are just set equal to each other, and they both have a 2 out front, so I can get rid of the 2. So I have this. Okay, and to isolate beta, we would think about it as dividing both sides by this, but in linear algebra, we take the inverse of all of this. So this right here, when I do all the multiplications implied there, I just get a matrix. And so I'm just going to multiply on the left-hand side by the inverse of that on both sides. And so now I get that beta hat is this. Okay. Now remember, beta hat here is, again, it's a vector containing both beta naught hat and beta 1 hat. Okay, and this will end up being that vector here, but it's just a bunch of matrix multiplications. Okay, so now we need to carry through with these matrix multiplications. Okay, so we already have the expression for XTWX. We're going to take its inverse, but we already have that. That's what we found already. Okay, we found that already up here. Okay. And so we're going to have to find the inverse of that expression as well as this expression right here. Okay, so xt times w times y. That's just going to be a vector here. Okay, and so we'll do both of these in turn. Okay, so XTWX, remember we found was this. And so if I want to take the inverse of that, the inverse of a 2 by 2 matrix, if you don't know how to do it, it's 1 over A times D minus B times C. Okay, and so that factor sits out front. Okay, that's its determinant, I believe, or 1 over its determinant. I can't remember. Doesn't matter. And then the matrix. So I just switch the two diagonal elements. I switch this, and then these two off diagonal elements get a negative in front of them. Okay, so now this is the inverse of XTWX. Okay, so now I need we found that part, and so now I need to find this part. Okay, well we already know what X looks like, or XT looks like. It looks like this. We defined that earlier. We defined W earlier, and then Y is just a vector with each observation. Okay, so the first thing I'll do is I'll just multiply the Y times the W matrix, and I'm going to get this. So now I need to multiply this times my X transpose, and when I do that, I get this vector here. Okay, so all right, so now that means if I multiply this and this to get beta, right, that's what beta is, which we already found, then I'm going to get this big expression. So everything here plus this factor right here, which my mouse doesn't want to highlight, but all of that is my X transpose WX inverse, and then this is my X transpose WY. Okay, so I'm just going to multiply. I'm going to multiply this second matrix by the first matrix, and then multiply, and then so I'm going to get that's a 2 by 2 and a 2 by 1. So I'm going to get 2 by 1, and then I'm going to divide both elements in that 2 by 1 by this factor that sits out front here, and I get this big ugly expression right here. And the top part, it's two fractions, so the top part is beta naught, and the bottom part is beta 1. Okay, so you have to kind of squint your eyes to see what that looks like. Okay, but we're just going to focus here on beta 1. Okay, so when this expression right here, again, when all of the w's equal 1, then this expression right here becomes this expression. Okay, so you'll have to kind of go through that for yourself, but everywhere where there's a w, just put a 1 in there and work through it. Okay, and what you come out with is this expression right here, right? So n times the sum of xy, but the expression that we want looks like this. So we're really, really close. Okay, we have a xy and an x squared in the numerator and denominator, and an xy and an x squared down here. Well, the thing that's different is up here, the n is under here. Okay, it's under the second term on both the numerator and denominator. But here it's in front of the first. So we just need to divide everything by n. So when I divide this by n, the n goes away. When I divide this by n, the n goes away, right? So I get these terms. But that means then that I have to divide this term and this term by n. Okay, and that's what I get there. Okay, and that's the expression that we're meant to show. All right, so that is it for this one.